Okay, so for now, we're taking as a Fourier series the expression for a function as an infinite sum in terms of these cosine and sine functions. These cosine and sine functions. So you got cosine of x, cosine of 2x, cosine of 3x, and so on. And same for the sines. So you've got an infinite sum consisting of those cosine and sine functions, and they've got various coefficients, an and bn, in front of them. An in front of the cosines and bn in front of the sines. And there may indeed be a constant term as well, which just for notational reasons or reasons of fitting the nice formulas together, that constant coefficient has a half in front of it, but there's nothing mind-blowingly important, deep going on there, really. So we introduced this last time, and these exist for functions that are periodic, as it's set up there for functions that are periodic with period 2 pi. So the function behaves in a certain way in the interval minus pi to pi, and then everywhere outside that interval, it's just repeating that same behavior. Okay. Now, there are some technical conditions that the function needs to satisfy, but I mean, most functions you encounter in the wild, in real life, easily satisfy these. These is quite extreme behavior that's being ruled out here. Okay. Functions having an infinite number of discontinuities in that interval. That's pretty weird behavior. Or functions having an infinite number of maximums and minimums inside that interval. We're not talking about those kinds of functions here. Okay, so it's interesting that the Fourier series do exist for non-continuous functions, functions which have a discontinuous jump in value. And what's explained down there below is that, well, in those cases, it's not that the series on the right is equal to the value of the function, but it does a good fair job. It's equal to half of the left and right. It's equal to the average of the left and right-handed limits as you approach that point of discontinuity of the function. Okay, so that's a nice equal-handed behavior of the Fourier series. Okay, so we described last time some of the theory underlying this, and we described how what makes it all fit together is that this family of functions f down here, which you're looking at just at the bottom of the page, so this consists of the constant function 1, all those cosines, and all those sine functions. That family of functions is an orthogonal family, meaning that when you pluck any two different functions out of that family and take their inner product, the inner product being the standard inner product in this function space here, which is to integrate the product of the two functions over the interval. So that family being orthogonal means when you pluck any two different functions out, take their inner product, you get 0. Okay, so they're all kind of perpendicular to one another or orthogonal to one another with respect to this standard inner product. And that led us to these formulae for the Fourier coefficients. So this A0, the ANs, and the BNs, so these are the coefficients appearing in the Fourier series. So a typical problem, or typical kind of calculation type problem that you encounter in these is you're given a formula for a nice function f, and the task is to determine the Fourier series. So that means to determine what the value of the coefficients are, what the A's are, and what the B's are. Well, they come from these formulas here. Okay, so you can these are integral formulae for A0, AN, and BN for n bigger than or equal to 1. You can also see them as instances of the inner product. Okay, so this, so we talked about this, but I'll just briefly write it down here. Using the notation that we have above with the angle bracket for the inner product, what you're seeing here is the inner product of the constant function 1 with f. And what you're seeing here is the inner product of the basis function cosine nx with f, and a 1 over pi in front of that. And here you're seeing 1 over pi times the inner product of sine nx with f. And seeing it this way is good because it kind of ties it into what the kind of picture or theory you already have from linear algebra. Okay, in linear algebra, first year and now in second year with Stephen, you talk about vector spaces. These vector spaces have bases. Particularly nice bases are orthonormal bases, or orthogonal bases at least, where the scalar product, say, talking about conventional vector spaces, the scalar product of any two vectors from the basis is 0. So all the basis vectors are mutually orthogonal. And then any vector from the space can be represented as a linear combination of those basis vectors. Now, the coefficients that arise in that linear combination will be given by the appropriate expressions to do with the scalar product. It will be the scalar product of that vector with the basis vector. Some approaches to the thing incorporate the 1 over pi into the definition of the scalar product. Some books don't. There's no universal agreement on what you should do there. However, one advantage of doing that, if the inner product, if this 1 over pi factor becomes part of the definition of the inner product, then that changes, it allows you to say a little bit more. This family of function then becomes orthonormal. So we already have it being orthogonal, meaning the inner product of any two functions from it is 0. But if you take that 1 over pi factor into the definition of the inner product, it then becomes an orthonormal family, meaning it's orthogonal, but if you take the inner product of any vector with itself, it's equal to 1. Okay? So it in effect says that this is a really standard basis. All the vectors are orthogonal to one another, and each of the basis vectors, or functions in this case, has length 1, has magnitude 1. So some books will set it up and treat it like that. Now, for our first kind of fully worked out example, we tackled the square wave function, so-called square wave function. So I'm still kind of reviewing what we did last time, so I'll try and, but it kind of leads on to what we're going to do now. So we looked at the square wave function. The square wave function is kind of just the periodic continuation of the Heaviside step function, which we were meeting with when we were looking at Laplace transforms. This is what we talked to last time. So that red graph there, the function which is alternatively 0 and 1, it's called the square wave function. And we found its Fourier series. We applied these integral formulae here, which we're looking at here, to this function. And we treated them carefully, and we got that the ANs were all 0. Yeah, the ANs were all 0. The A0 was 1, and the BNs were, well, the BNs, half of them were 0 and half of them weren't. So there was an even-odd thing going on with the index n, with the BNs. And so that allowed us to prove what's written down here in the bottom of that page there in equation 3.12. We derived that Fourier series for the square wave function in the lecture last time. Okay, so that was our first worked out example. Now, continuing right on from that, see a little bit up here, another little example in example 3.5. So just before moving on to the next section, I just want to discuss some of those, some of that thing. So we have this square wave function. So we have the square wave function f, this one here. So it's really just the Heaviside step function, really, under another name, really. So it's 0 for every x less than 0, and it's 1 for x beyond 0. But we're just looking at it in this interval from minus pi to pi. Okay, and so last time we proved it has this Fourier series. sum over m, 2 over 2m minus 1, and then it's the sine of 2m minus 1 times x. Then m goes from 1 to infinity. So it's the constant a half plus this infinite summation of sine functions. Now you're summing over this index m, but of course, the way m occurs in the thing here is it's 2m minus 1, 2m minus 1. So that means you're just going to pick out all the odd integers in this actual expression here. So we'll have 2, well, when m is 1, it's going to hit 1 first. So it'll be 2 times sine of x, 2 over 3 times sine of 3x, 2 over 5 times sine of 5x, and so on. You're only going to pick out those odd integers. Yeah. You have this 1 over pi here. So it'll be 2 times sine. I should have let's put the 2 outside. The 2 outside there. So it's sine of x plus 1/3 sine of 3x plus 1/5 sine of 1/5 sine of 5x, etc. Yeah, everybody see that? So you just get those sine functions where you've got an odd integer. Now it's equal to the square wave function everywhere that the square wave function is continuous. Now the square wave function has this one point of discontinuity at x equals 0. And what value does the Fourier series take at x equals 0? Well, by the way, it's not really important what the value of the square wave function is at 0. In the definition I've written up there, I've given it the value 1 at 0. But equally well, you could have given it the value 0, or you could have given it any value you want, really. The values of these functions at individual isolated points isn't really relevant. But what value does the series take? Well, when you evaluate it at x equals 0, all these signs disappear, because it's just sine of 0 to 0. So the only thing you're left with is the 1. And that seems a fair choice to make, because if you look at the limit from the left-hand side, as you come towards the point of discontinuity, the limit is 0, because the function is always 0 there. And if you look at the limit as you come at that point of discontinuity from the right-hand side, you got a limit of 1, because the function is always 1 to the right-hand side. So the average of 0 and 1, of course, is a half. So that's nice kind of fair behavior of the Fourier series there. Now from this Fourier series, we can get a really nice result because of the presence of pi here. See pi here kind of hiding away in the middle of the formula. We can get a nice result about pi, which you may or may not be familiar with before today. You may have seen it before and then forgotten about it. I'm always kind of, I still don't understand. I can't say I've got a great understanding of this result. I think it's quite, if you just stare at it and think about it for a minute, you realize there must be a hell of a lot of deep understanding that you can gain from really appreciating why this result is true. But we'll see what it is about now. So we'll just evaluate the Fourier series. What we're going to do is evaluate it at x equals pi over 2. Yeah? Now, when you look at the left-hand side is f of x, the square wave function. What is the square wave function at pi over 2? Somebody shout it out there. F of pi over 2 is? Someone say 0? 1. 1. Definitely 1. Give the person who said 0 a flick in the air or something. F evaluated to pi over 2 is, of course, 1. Just look at the original function. But when you look at the Fourier series, you see something a bit more interesting. Well, you've got a half there, that constant a half. You've got your 2 over pi. And then you've got sine m equals 1 to infinity. 1 over 2m minus 1 times the sine of 2m minus 1 times pi over 2. Now, sine of 2m minus 1 times pi over 2 has a nice value, or values. There's two possible values of this. Two possible values of sine of this are +1 or -1. Good, because you're looking at an odd multiple of pi over 2. So you think of the unit circle in the complex plane, an odd multiple of pi over 2. This means you're either pointing up on the vertical axis or pointing down on the vertical axis. So the sine value is going to be plus or minus 1 accordingly as this m is odd or even. Okay. There's going to be 1 over 2m minus 1. M goes from 1 to infinity. So it's just going to be a plus sign or a minus sign. So you just figure out how's it happening. Well, the first one, when m is 1, you've got sine of pi over 2. So that's going to give you +1. And then the next one, m equals 2, will be down below, will give you minus sign. And the next one, when m equals 3, you'll be up above, which will give you a +1. So it's the odd m that are giving you the positives and the even n which are giving you the negatives. So if you make the power on -1, there'll be m plus 1, that'll give it to you. Now, if you just want to understand it a little bit clearer, just unravel the summation there for a few terms, which is 1 minus a third plus a fifth minus a seventh. So you see what it is? Plus a ninth minus 11th and so on. But this thing is quite easy. It's just equal to 1 on the left-hand side. So sorry, I should have put a dot, dot, dot. This is an infinite sum here. So it's the, what's that summation there? That's the alternating series of the reciprocals of the odd integers, the positive odd integers. 1, 1 over 3, 1 over 5, 1 over 7. And when you rearrange all of this, you take the minus a half over there, so you got a half over here, you multiply both sides by pi over 2. Well, you get pi. Let's quote it in terms of pi. Pi is 4 times this series. I think that's kind of neat. The reason I think is, well, okay, so it's a very nice formula to see. It's a formula for pi. Pi is very important to do with circles. Ratio of the circumference to the diameter of a circle, of course. But I think it's kind of cool because, like, when you look at this side, I mean, where is the circle over here? Got 1 minus a third plus a fifth minus a seventh plus a ninth. I don't see, you know, this side, the right-hand side doesn't scream out, you know, I've got something important to do with circles. I can't see it off the top of my head. So I think it's kind of, you know, there's a lot to understand if you want to investigate this a little bit more and try and, you know, come up with a good explanation of why, or you know, an explanation of the meaning of that result. I think there's a lot to get from it. I mean, this is a derivation of it here, but you know, I think there's a lot more you can get from this. So that's a nice formula for pi. Okay. Underneath that section, there on page 61, there's a little bit of generalization. Okay, so up to now we've just been looking at Fourier series in the interval minus pi to pi. There, I give a generalization where you weaken the constraint on just looking at it from minus pi to pi, where you can look at it on any interval centered on the origin, any interval from minus t to t. Okay, and it just comes about from making a substitution rather than considering the original variable t. You just, or rather than changing the original, rather than considering the original variable x, you introduce a new variable t. This is the proportion x over capital T, and you're adjusting by pi. So that'll take you from one representation to the other, and you make the appropriate adjustments in the formulae for the Fourier series coefficients. Okay, we'll return to this idea in more detail later when we look at other generalizations of the Fourier series. But in most of the examples here, we'll still just stick for the moment on the minus pi to pi interval. Okay, but we will revisit this a little bit. Okay, any questions or queries on anything at the moment? Just pause a little bit just before we go on to the next section on odd and even functions. Any questions or queries about it at the moment? If you haven't seen this formula for pi before, I'd suggest, there's some good pondering to be done on it, on why it's true, and what it's telling you. And I mean, every bit of mathematics is connected to every other bit, kind of. So it's not surprising that we see these things. But yeah, question. What have you gained from it? Well, in some ways, I'm saying I'm not sure what you've gained from it, because I don't have an amazingly good insight into it myself. I think I did before, but I think I might have forgotten what that insight was. Since you raised the question, what do you think of that formula? Interesting. Yeah. I think it is. Because I think you should ask the question, why should this expression over here, why should that have anything to do with a circle? That's, That's okay, that's okay. Okay. So the next section we move on to then is 3.3. It's odd and even functions. Well, actually, no, sorry. Since he did a challenge for me. Okay, here's an actual answer to that question. What have you gained from this? What you have gained from it is a way, if you believe it, that the sum of this infinite series will equal pi. What you have gained is a way to approximate pi to any level of approximation. I mean, you can set up pi as being the ratio of the diameter to, or the circumference to the diameter of a circle. You can set about measuring that physically by tracing an actual circle in the ground, measuring it, and blah, blah, blah. But that'll only get you so far. That can only get you an accurate answer, because at the end of the day, it's impossible to draw a real circle. It's impossible to measure anything exactly. But the right-hand side of this, you can calculate any partial sum of this exactly. Okay, so you can sum up minus 1 to the power k plus 1. So I'm looking at it here, divided by 2 times k. 2 times k minus 1. I can sum that for k in the range, say, the range 1 to 10, we'll sum that from k equals 1 to 9. And then what you have to do to it, you multiply it by 4. Oh, yeah. So the way that formula calculates is just as a big fraction. If you actually want to see the decimal expansion of it, stick an n around it. So 3.25 is the approximation to pi that you get from the first 10 terms of the series. Yeah. James stole my next sentence. The more terms you do, the more accurate it gets. 3.15. You can compare it with the actual value of pi. Oh, pi, yeah. If you go 100, so it's actually an example of a fairly, it's actually quite a slowly converging series compared to other series that are out there for pi. Because you go 100 terms, you still only have it accurate to one decimal place. If you went 1,000 terms, 1,000 terms only gets you 2 decimal places of accuracy. It's wrong in the 3rd decimal place. Okay, but in the absence of any other series, it gives you a way to calculate pi, and to calculate the digits of pi. If you take in enough terms in the series, you'll get more and more accuracy, more and more decimal places of pi. There are infinite series formulas for pi that converge much quicker, which are better. Okay. So the answer to your question is one answer is it gives you a way to approximate pi to any desired accuracy. Okay. Okay, so coming back to the next section on odd and even functions. What this section is about, section 3.3, is exploiting some features of the function f that will make it easier to find the Fourier series. Okay. So section 3.3, exploiting features that the function f might have to understand the Fourier series. Now, what are these features that we're talking about? Well, the features are to do with being odd or even. So being odd or even is special behavior for functions. Now, this is not the odd or even integers, which is to do with an integer being divisible by 2. This is a different use of the word odd or even functions, which is to do with the behavior of a function on positive or negative arguments. So here are the two definitions. Maybe you've seen them before, maybe not. An even function is one where f of minus x is always the same as f of x. An odd function is one where f of minus x is always the negative of f of x. Now, these definitions have a very clear geometric interpretation. An even function, well, it can do a bunch of stuff. You can have, any kind of behavior it wants on the positive half of the interval, but on the negative half of the interval, according to the definition, it has to behave in exactly the same way. So the behavior on the negative half will have to be an exact copy of the behavior on the positive half. See if I can draw that. Yeah, I will in a minute. Hang on. So you've got an exact copy. You've got an exact copy, mirror image on the left and right. Looks okay. So that's what an even function looks like. An odd function again can do anything it wants really. Over here. But on the other side, how it behaves on the negative arguments, it has to behave the negative of how it behaves on the positive arguments. So it's going to come down here like this, then go up, down there, and then go up and cross the line there, and then do something like that. Okay? So being odd or being even is quite special behavior. Most functions won't, most random functions won't be either, of course. They're not opposite properties. If something is not odd, it doesn't mean it's even, and vice versa. But they are, they're almost exclusive properties. If the function's even, it's not going to be odd except for one special case. What's that special case? Kudos to the person who says the special case for a function that is odd and even. Sorry? No, just real valued function. Zero function. Yeah, the constant function 0. Constant function 0 is simultaneously even and odd, but for entirely uninteresting reasons, really. Yeah, no, I said at the start, it didn't have anything to do with being divisible by 2. It's just a different use of the word. It's not related to being divisible by 2 or anything. It's related to its behavior on the positive and negative arguments. Those definition in 3.1. Yeah, okay. We did go through it just a couple of minutes ago. That's okay. Okay, so even function is one which agrees on minus x and x. An odd function is one which takes the negative of how it behaves on the other one. So f of minus x is minus the f of x. So on. Now, the reason we're looking at this is because even functions and odd functions, they have simplified Fourier series. Simplified Fourier series. So if you look at example 3.6, the cosine function is even. Think about the property of the cosine function. Cosine of minus x is always going to be the same as cosine of x. So cosine is an even function. And the sine function is an odd function. Sine of minus x is minus x. What is x to the power n, the kind of polynomial term function? F of x equals x to the power n. Is that odd or even? Could be odd. Could be even. Well, if n is a integer, it's going to be even for even n, and it's going to be odd for odd n. So that question, those sentences are potentially confusing because the words even and odd are being used in 2 different ways. So even, this even here refers to the even function. So that's even as in definition 3.1. This even is the usual even that, you know, the divisibility by 2. And in the same way, this odd here has to do with definition 3.1. And this odd here is the usual integer definition of odd and even. Now, don't blame me for this setup. I didn't choose to use these words like this for my own amusement. It's the way the world does it. So I guess this is a connection between the two. You know, it's a way to remember. It's nice that the x to the power even n is an even function and x to the power of odd n is an odd function. It'd be quite confusing if there was the opposite way around. Okay. Now, even and odd functions, they behave in a regular way according to multiplication of functions. A multiplication of functions is is of course an important operation here. Why? Because it's at the heart of the definition of our inner product. The inner product we're using here is we're integrating the product of the two functions. So multiplying functions is a very important operation here. And how even and odd functions behave under multiplication is recorded in theorem 3.2. Well, having just said that there's a nice connection between the two uses of even and odd, we have to again be aware that here there's a difference in behavior. So this new use of odd and even for functions is behaving differently here than odd and even for integers. If you look at what it's claiming here, and we can prove these fairly easily, we will do now in a moment, the product of two even functions is going to be an even function. The product of two odd functions is going to be an even function. And the product of an even and an odd function is going to be odd. Now, this is different to how odd and even integers behave. The product of two odd integers is again an odd integer, isn't it? But here, the product of two odd functions is an even function. So there's potential for confusion. So let's see, you know, does it take much to prove theorem 3.2? Well, not really. I mean, really what you're seeing here is the effect of what happens when you multiply two positive things or two negative things or a positive and a negative thing. It's really nothing more sophisticated than that. So if you took u1 and u2, if you let those u1 and u2 be two even functions, and let w1 and w2 be two odd functions, well, we can prove these things fairly directly. How does the product u1 times u2, how does that behave on minus x? Well, we can track how it behaves on minus x by seeing how u1 behaves on x and u2 behaves on x. Sorry, minus x. So here we're evaluating a product function on minus x, so it's the product of the two functions evaluated on minus x. But I've just said u1 and u2 are even, so this is the same as u1 of x times u2 of x. And so that's the same as u1 times u2 of x. So from start to finish there, you see the product function u1, u2 agrees on minus x and x. Therefore, it's an even function, according to definition 3.1. Okay. So therefore, u1, u2 is even. If you try and do the same thing with the w1 times w2, w1 of minus x times w2 of minus x, well, because both of these functions are odd, you both you get a minus sign introduced to both of them when you evaluate them at minus x. But of course, those two minus signs are going to together give you a plus sign. So this is just w1 of x times w2 of x, which is indeed w1 times w2 evaluated at x. So again, the product function is agreeing on minus x and x. So w1 times w2 is an even function. If you take a u and a w, a u1 and a w1, do the same thing, you'll find you just get one minus sign occurring. So we can also see that if you take u1 times w1, evaluate it at minus x, you get minus u1 w1 of x. I've skipped the intermediate steps there. But there you can see that it's odd. So the product of an even with an odd is odd. Functions, that is, not integers, of course. So you just have to remember that the two uses of odd and even for functions and for integers, they're kind of related, but they kind of conflict. So there's potential for confusion. So you just need to check the definitions carefully. They're not unconnected, but they're not connected in everything. So it's the worst of both possible worlds, or the best. Okay, now how is this relevant to Fourier series? Well, cosine is even and sine is odd. And if our f function we're considering is even or odd, then those products, f times a cosine and f times a sine, we'll know whether they're even or odd, okay, accordingly to, it will depend on the status of f. Now, what happens when you come back to the little sketch of an even and an odd function I did a few moments ago? If I integrate this function from minus pi to pi, or well, let's talk about the odd function first. If I go from minus pi to pi on the odd function, what am I going to get? Yeah, we're going to get 0, aren't we? Okay? Because if you integrate it across any interval that's centered on the origin, see, one half of it is going to behave in one way, but the other half of it is going to behave in the same way, but with the opposite sign. So every positive part of area here is going to occur with a negative sign, the same absolute value of area, but it's going to occur with a negative sign down here. And here in the positive half, you'll get a negative bit of area there, but you'll get the same size of positive area back here. So they all cancel out. That's as long as the interval you're integrating over is centered at the origin, which minus pi to pi obviously is. If you integrate the even function, well, how does that behave? A positive bit of area here again occurs with a positive sign there. Yeah, a negative bit of area there again appears to a negative sign there. Here's a positive bit of area on the left. You pick it up as a positive area there on the right. So the integral, well, whatever you get on one side of 0, you also get the exact same thing on the other side. So you can simplify, if you like, or just re-express this as twice times the integral over just one side of that function. But where I'm talking about the same function in both cases, yeah. This function there. So it's these kind of integrals that occur. Sorry, question. An even function is always exactly symmetric. The odd function is symmetric as well, but it's reflection in the vertical and in the horizontal. You have to compose the two reflections, which is the same. Also, it's called a central inversion in the origin. If you join the point here to the origin in a straight line, you just continue the line out the other side to the same distance, and you get the image point. It's called central inversion in the origin. So the symmetry that this function up here has is reflection. Okay, reflection in the y-axis. Here, the symmetry that you have is central inversion in the origin, which is the same as the composition of reflection in the y-axis and the x-axis. Okay. Now that fact about integrals there is recorded in theorem 3.3. If g is an even function and h is an odd function, then the integral of the odd one gives you 0. The integral of the even one can be written as 2 times the integral over the positive part. And these have consequences. So I'll just finish by looking at these results. The consequence of this for Fourier series is that if your function g is an even function, its Fourier series doesn't have any sine functions in it. It just consists of the cosine functions and the constant one, perhaps. If your function h, as it's written here, is an odd function, it means its Fourier series doesn't have any of the cosines in it. It just has the sine functions in it. And in each case, you can adapt the formula for the remaining coefficients that do appear into the 2 times the integral over the positive half, should you wish. So that cuts down the amount of work involved in finding the Fourier series for an even or an odd function, because ahead of time, you know that half of the Fourier coefficients aren't going to be there. Okay. Okay, we'll pick this up next week. And in the tutorials this week, we'll do lots more examples with it and continue with the study of it. Okay?